A vertical pipe of height 1 meter carrying oil of specific gravity 0.8 tapers uniformly from 0.2 meter diameter at the lower section to 0.1 meter diameter at the upper section. The vertical gauges installed at the lower and upper sections read 6 into 10 power of 4 Newton per meter square and 5 into 10 power of 4 Newton per meter square respectively when discharge of oil is 30 into 10 power of minus 3 meter cube per second. Here the loss of head between two sections is, here a vertical pipe is carrying an oil of specific gravity 0.8 and we don't know whether it is flowing from lower section to upper section or flowing from upper section to lower section, but we can apply Bernoulli's equation between the two sections at lower and upper section. Let us say at lower section with suffix 1 and upper section with suffix 2, and here Bernoulli's equation is given by P1 by rho g plus V1 square by 2g plus Z1 and P2 by rho g plus Vt square by 2g plus Z2 plus head loss. So here already the two vertical gauges installed at the lower and upper end, those read P1 is equal to 6 into 10 power of 4 Newton per meter square and P2 is equal to 5 into 10 power of 4 Newton per meter square. And here the lower section diameter is 0.2 meter and upper section diameter is 0.1 meter and Q is equal to the discharge of oil is equal to 30 into 10 power of minus 3 meter cube per second. So here the discharge of oil is given by A1V1 or A2V2, that is area at the section 1 into velocity at the section 1 or area at the section 2 into velocity at the section 2. So here from this equation we can find out V1 and V2. Here V1 is equal to Q by A1 and here 30 into 10 power of minus 3 by pi by 4 d square, where diameter at the lower section is 0.2 square, which gives a value of 0.955 meter per second. In the same way we can find out V2, which gives a value of 3.81 meter per second, and here Z1 is equal to 0 and Z2 is equal to 1 meter, or the difference between the upper and lower section Z2 minus Z1 is equal to 1 meter. So now substitute all the values in the given equation, and here we will have to find out the density of the oil. Density of the oil is equal to, here specific gravity of the oil is 0.8 and the standard density of standard fluid density is 1000, which gives 800 kg per meter cube. Now substitute all the values in the equation, we can get here head loss, so which is equal to 0.423. Generally here we get minus 4.423, but here they didn't ask that head loss at the upper section or head loss at the lower section. Just the given question is the loss of head between two sections. So the loss of head between two sections is 0.423 meter of oil. So in the option, the right option is B. A cylindrical shaft of 100 mm diameter rotates about a vertical axis inside a fixed cylindrical tube of length 2 meter and 106 mm internal diameter. A lubricant of dynamic viscosity 2 poise fills the space between the tube and shaft. The shaft rotates at a speed of 240 rpm. Assume linear variation of velocity across the gap. The power required to overcome the resistance is. So here the options are. So here overcome the viscous resistance. 6.6 watts, 66 watts, 3.3 watts and 33 watts. And coming to the solution, here a cylindrical shaft of 100 mm diameter rotates about its vertical axis inside a cylindrical tube, and this gap between the cylinder and shaft fills with a oil of viscosity how much? 2 poise. And here the shaft diameter is 100 mm and this is the tube diameter is 106 mm and tube length is L and tube length is 2 meters. So here we'll have to find out the power required to overcome the viscous resistance. Here power required to overcome the viscous resistance is given by the shear force into the the tangential velocity of the cylinder. So tangential velocity of the cylinder is pi d n by 60, and here the shaft rotates at a speed of 240 rpm, so that here the diameter of the shaft is 100 mm, that is 0.1 meter, and here it is 240 by 60, which is equal to nearby 0.4 pi meter per second. So this is the tangential velocity of the cylinder. Now we'll have to find out the shear force, where shear force is equal to the stress developed in the fluid into the shear area, that is pi dl. Okay, here the stress developed is here the stress varies linearly, so that we can apply here tau is equal mu into du by dy, where dy is the 106 minus 103 by 106 means 100 by 2, which is equal to 3 mm. That is, this is the gap between cylinder and shaft. So here dy is equal to 3 mm and du is given by 0.4 pi. Now substitute all the values here, which gives, and here already we know that mu is equal to 2 poise. 2 poise is nothing but 0.2 Newton second per meter square. 2 poise are 0.2 Newton second per meter square. Now substitute all the values in the shear stress equation. We get here 0.2 into pi into 100 into, so this is 0.1 into 2. So it gives a value of, here tau is equal to mu into du by dy, that is 0.2 into 0.4 pi by 3 mm, that is 0.003 meters, which gives a value of 0.266 into 10 cube Newton per meter square. Now substitute all the values in shear force. So here Fs is equal to tau into pi dl, that is 0.266 into, here total value is 83.6 Newton per meter square. Now shear force is equal to 83.6 into pi into 0.1 into 2, which gives a value of 52.63 Newton. Now substitute this value in power required, that is P is equal to Fs into V. So here P is equal to 52.63 into, where V is the 0.4 pi, so which is equal to 66 watts. So in the option, the right option is B. List 1 and list 2. Here list 1 consists some equations and list 2 consists assumptions made in the respective equations. Here the Fourier equation, the list 1 consists Fourier equation, Newton's law of viscosity, LMTD heat transfer equations for long fin. So here Fourier equation, the assumption made in Fourier equation is homogeneous material and internal heat generation. So it matches with the term B. And Newton's law of viscosity related with laminar flow, that is C, and LMTD heat transfer. In LMTD heat transfer equation, the assumption made is overall heat transfer coefficient is constant throughout the body. And here heat transfer equation for a long fin is the temperature of the end equals to that of surrounding fluid, so that it is 4D. So in the options, the right answer is A.